All right. So today we want to just talk about something, and today's lesson is actually pretty simple. It's fairly straightforward, but it's going to pave the way for handling difficult cases. All right? So the concept today is something called formal charge. Formal charges. So you've learned in this unit about how atoms form hybrid orbitals to form molecular compounds. But if you've been paying attention, we've also been breaking some rules, right? We've been breaking some of our traditional rules, which we've already talked about, right? Not everything's always making the right number of bonds compared to what we've been taught. You can turn that back on, by the way, if you like. You don't have to, but if you'd like. So I'd like you to draw the nitrate ion here, please. Nitrate. Can anyone remind me what the formula for nitrate is? Don't worry if you don't know it, but does anyone remember it from grade 11? NO3. And what charge does it take? -1. Okay. So take a moment and draw a Lewis structure for the nitrate ion in the space provided, please. Oh, I hope they come around with coffee for today. I sell my children for coffee right now. They're not the good ones, you know. Oh, she's not even here. Throw it in. All right, nitrate, talk to me. What do we got? What do we got? Guide me. What should we do first? Count all the electrons. Okay. So if I'm counting all the electrons, how many does nitrogen give me? Yeah, 1, 2, 3, 4, 5. 5 electrons. Okay. 3 times oxygen, which gives me how many each? 6, for a total of 18. And then, of course, it has a -1 charge. So that is 1 electron. And that, my friends, gives me a total of 24. 24. Okay. So, as my friend Albert Camus would say, 24. Electron. What do we think electrons is in French? It's going to be like électron, right? Something like that. Does anyone know? Anyone have a science education in French? Is it? Okay, do we want to find out? I'm curious, all right. Okay. Oh.
Électron.
Yeah, can confirm. Yeah, I like it. Thank you.
Électron.
Yeah, it won't let me do your tenants, what you want me to.
That's oh, my tendency then.
Yeah.
Damn. Okay, I'll be back there in a moment. Okay, one sec. Ready?
Électron. Électron.
Electron. Casual.
Électron.
Electron. Formal.
Électron.
Kind of sounds the same. Kind of sounds the same.
Électron.
Okay. What about proton?
Proton.
Proton. Proton.
Neutron.
Neutron.
Atome.
Atome. Les atomes ont des électrons, des protons et des neutrons. Ah, okay. Anyway, mon Dieu, voici des électrons. Okay, so combien d'électrons? Il y a 24 électrons en le nitrate ion. Anyway, okay. So, I had to teach French immersion science for 3 horrible weeks, and it was awful. No. But it was terrible. I was so bad. I didn't know it was a French job when I applied for it. And then after I got the job, they're like, "You speak French, right?" And I was like, "Yeah." But I was desperate for work, so I was like, "Oh, oui, je parle français comme un francophone. J'aime français beaucoup." I was like, "Bonjour, mes élèves, comment ça va aujourd'hui? Je m'appelle Monsieur Orlando. Anglais, English today? What if we did today in English, kids? Everyone comfortable with that?" And they would say yes, and I'd say, "Oh, good, me too." And then we did the lesson in English, and I would say, and then I would do. There was no Google Translate at the time or anything like that, so I'd get the dictionary out, and we'd look the words up and say, "Okay, we did the lesson in English, but let's make sure we know the vocabulary in French, right? Okay, good. Électron." So this was an ecology unit, so it was like niche was good. I was like, well, that's got to be good. But anyway, so yeah, it was not good. It was pas bien, if you know what I'm saying. It was trop mal, if you know what I mean. Too mal, too bad, no good, very bad. Okay, nitrogen goes in the middle, oxygen goes in each direction, and then we're going to put our valence electrons on. Is that comfortable for everyone, or am I going too fast? Tell me if I'm going too fast. Too fast? That's not helpful. Okay, so could we just engage sincerely? That would be helpful. And what do we do now? Count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that is the correct number, right? But what doesn't have a complete octet? And can we give it one? It's not, we don't have an odd numbered situation or something here. Sure we can. What do? Yeah, you form a double bond. So that doesn't have to be a lone pair of electrons. That can be a double bond. And we would say, okay, we draw square brackets around it. We give that a -1 charge, right? If it had been like there were only 23 electrons, then you'd be out of luck. Then there's nothing you can do to get it to be perfect. But this can be good, right? We make that double bond. We're good to go. All right. Fantastic. Here's the thing. This breaks our rules. Why does it break our rules that we learned in grade 10 science and grade 11 chemistry? Yeah. Yep. Yep, absolutely, which means we normally think of nitrogen as making how many bonds? 3, right? But here it's making 4. And we normally think of oxygen as making, how many bonds do we normally think of oxygen as making? 2, right? We think of it as needing to get 2 more electrons to get to the valence. So one of the oxygens is behaving like we expect it to, but these other 2 seem to be making one fewer bond than they should. Does that make sense? Does that feel okay? So we'd say nitrogen, normally 3 bonds. Oxygen, normally 2 bonds. That's going to be important information. Is there anyone who's not comfortable how I got that? We know that a complete octet is how many electrons? 8. So if nitrogen normally has 1, 2, 3, 4, 5 electrons, then to get up to 8, it would have to make 3 bonds. Oxygen normally has 1, 2, 3, 4, 5, 6 electrons, not 7. I don't know why I tried to keep talking. 6 electrons, which means that it would need 2 more to get to 8. So again, now is a really good time to tell me if you're not comfortable doing that, because you're probably not the only one if you're confused. Okay. Then we're going to assume that you can do that and look at how many bonds something normally makes. Let's just look really quickly. We're not going to do this every time, but the middle nitrogen, how many lone pairs does it have? No lone pairs, okay? How many sigma bonds is it making? 3, yeah. And how many pi bonds is it making? 1. What's its hybridization state then? sp2, very good. Can't be sp3 because sp3 would be if it was making no double bonds, right? No pi bonds. But since it's making 1 pi bond, it's sp2. Okay. If we did its electron configuration, we'd say it's 1s, right? And then we'd say it's 2sp2. How many actual orbitals does that give us? 3. 1, 2, 3. Because what's left behind? 2p. And what will those look like? Well, there's no lone pairs. There's 3 sigma bonds, so that would be 3 sigma bonds, and there is a pi bond. I'm even going to highlight that. The sigma bonds are found there, and the pi bond is found there. Does that feel reasonably comfortable for everyone? Pi bonds happen out of p orbitals left behind. Sigma bonds and lone pairs go in hybrid orbitals. That's okay? Speak now or forever hold your peace. I'm here. Okay. Let's talk about the 2 single bonded oxygens. Right? So these guys down here. How many lone pairs do they have? How many lone pairs does this guy have? 3 lone pairs. How many sigma bonds is it making? How many pi bonds is it making? 0. What will its hybridization state be? sp3. Right? Because it's not making any pi bonds. So it would be 1s, right? And then it would be 2sp3. And how many orbitals do we actually get from that? 4. Because the s and then all 3 p's will make 1, 2, 3, 4 orbitals. And what have to go in there? 3 lone pairs. How do I draw 3 lone pairs? How does one draw 3 lone pairs? So if these were our lone pairs, what do I have to put there? Yeah. Yeah, 2 electrons, right? One with positive spin, one with negative spin. Okay? And then the sigma bond will go here, and what's that look like? Okay, cool. And then the double bonded oxygen. How many lone pairs in the double bonded oxygen? Good. How many sigma bonds? 1. And how many pi bonds? Excellent. So its hybridization state would be sp2. And so it would also be 1s full, 2sp2. How many orbitals do we get in an sp2? Yeah, 3, very good. And then what would still be there? Yeah, and how many of those? Excellent. Very good. And so we'd take those 2 lone pairs, the 1 sigma bond, and the 1 pi bond, right? And you can fill that in. What do the lone pairs look like? 2 electrons, yeah. The sigma bond is 1 electron. The pi bond is 1 electron. Okay, that's just review. Does that feel comfortable? You should be able to do that from a Lewis structure. Yeah. Sorry, could you say that again? Yep. Yep. Okay, so that's a good question. This will be to an oxygen, right? So this will be like with that, right? Then this one will be with another one of those, right? And then this one will be with this guy. And this one will be with that guy. Does that make sense? And that's how you actually get the bonds. So there's your double bond there. A sigma bond between them and a pi bond between them.
Last call for chess sign up. Anyone
Chess. Folks, would you be more likely to sign up if Mr. Kelford did a handstand?
Not happy today. Holding too many things. I'll hold them for you.
Would you be more likely to do it if Mr. Calford played a song on the piano?
I think somebody has spam Hannah Waters and Kiki McFinger. I don't think they've signed up. Especially since Kiki's gender has been marked as frog. So that's...
And Kiki, I believe, does not go to the school.
I believe that's also another reason. All right. Oh, yeah, she does. Kate just went up and signed up. Yeah, that was fun. And then today, Calvert was like, play the chess tournament.
That was my little song, my little chess tournament song. Did you like it? Okay. Okay, let's focus in. Shh. Now, here's what I want to note. Here's just what we want to note. This is 1 fewer than N normally has, right? How many valence electrons does N normally have? 1, 2, 3, 4, 5. How many does it have here? 1, 2, 3, 4. Okay. This is 1 more than O usually has. And this has the normal number of electrons. Does that make sense? Again, tell me if it doesn't. Are we okay with that? Okay. So now we're just going to formalize that. Everything we just said with words, formal charge is just doing that, but mathematically. We're just going to define how many electrons each thing has normally. So we're going to talk about how we calculate formal charge. So to calculate formal charge, we use this formula. And let's take a look down here. The calculation is this. Okay? Okay, so the typical formula is the valence number of electrons minus how many bonds it's making. It doesn't matter which type. It doesn't matter if it's the sigma or pi bonds. That's number of bonds. Minus the non-bonded electrons. Boy, I don't like that apostrophe there. I hate when people put an apostrophe. Like, I hate when people are like, hey, remember the 90s? And it's like, we're not talking about something belonging to the 90s. That should be written like this because we're not writing the 1 and the 9 in front of it. You know what I'm saying? Or when people are like, the Orlandos, not saying something that belongs to us, but like you'll see this written on people's houses sometimes. And it's like, it's the Orlandos. And you're like, I mean, I guess you could say it's the Orlando's house, in which case that's what you mean. But if you just mean that the Orlandos live here, then really you mean that, right? Anyway, I would never put my name on a sign out front because I assume people would egg my house. Anyway. Right? That's what I'm saying. Have you ever egged a house? I never egged a house. I've never egged a house. You want to? And you were born to egg somebody's house, weren't you? And if I check my security camera one day, which I've never once done, I have security cameras, I don't even know the password. Full disclosure. Full disclosure. So,
That's way more security.
so I have no idea. I don't. The thumb, right? The thumb. I know my Microsoft password. Wouldn't you like to know? It is Ange is annoying. 1, 2, 3, 4 question mark exclamation mark. It used to just be Ange is annoying, and then they made me add all this other stuff to it. Anyway. You're going to be shocked when you discover that really is the password. No, it's not. There's no question mark. Anyway. I'd figure it out. Right? Like, there's got to be a reset your password thing. Right? In fact, that happened awfully. Like, not joking at all. There was a car accident. Somebody was killed outside my house last year, and I was able to get footage. So I had to do like but it was that thing. I was like an old man, you know, like every old person in your life is like, I need help with my phone, and you're like, oh God, no, please no. And then you're like, okay, there we go. What's your password? And like, I have no idea. And you're like, of course you have no idea. Why would you have any idea? And then you finally get through that, and you're like, okay, no problem. They've sent the reset to your email. What's your email password? And they're like, I have no idea. And you're like, ah! And then before you know it, you're on the phone with Google. And if you haven't been on the phone with Google before, you haven't lived, let me tell you. Anyway. Yeah. Yeah, and now you're locked out. Yeah, it's brutal. It's brutal. Okay, so let's take a look. Just some examples here. All right, we're just going to look at some examples here. In this case, it's carbon making how many bonds? 4 bonds. Okay. So if we were looking at this, we'd say carbon has a valence. This is just its normal number of electrons, right? This is the count over from the left bit. So this is like the count from left on periodic table, right? This is like the expected number of electrons. So if you look here, we know carbon normally has 4 electrons. And then we're going to say, okay, we're going to subtract the number of bonds, which in this case is 4. And we're going to subtract how many lone electrons it has. Does it have any lone electrons? None. So it has a formal charge of 0. A formal charge of 0 means, thank you, it is making the expected number of, it has the expected number of electrons. So any Lewis structure you ever drew in grade 10 or grade 11, where you just followed the rules, where I said carbon likes to make 4 bonds, nitrogen likes to make 3 bonds, oxygen likes to make 2 bonds, all of those, everything would have a formal charge of 0. If something is quote-unquote following the rules, it will have a formal charge of 0. Okay? So you actually don't have to check. Anything that's doing what it should do, formal charge is 0. All right? So if the formal charge is 0, it's following the rules. Now, if we look here, this one isn't following the rules. What do we notice? In this example, carbon is making 3 bonds, and does it have any lone pairs of electrons? No. So, if we followed that through, we could follow this step, and we could say, okay, carbon has a valence of 4, right? And that means we'd expect it to make 4 bonds, or have some lone electrons, but it's only making 3 bonds, and it doesn't have any lone electrons. So when we do that math, it leaves us with a leftover charge of plus 1. This means that this has a formal charge not following the rules. Now, to be clear, what this isn't is plus 2, because this is 2 away from having a full shell, right? But that's not what formal charge is, right? Formal charge is telling you how far away from the expected number of electrons it has. How far away from the expected number of electrons. We expect carbon to have 4 electrons and make 4 bonds. 4 of its own, make 4 bonds. In this configuration, it's only making 3 bonds, right? So it is 1 away from the expected outcome. Does that make sense? 1 away from the expected outcome, yeah. The answer is all these things can sometimes happen. We're going to learn that anything with a formal charge doesn't normally happen, but you can make them happen. Is that your answer? So normally things follow the rules. In 99.9% of compounds, things follow the rules. But 0.1% of the time, they don't follow the rules, and that's when you get a formal charge. These things are all less common, or there's charge involved, which we'll get to, because there's some very common things that have formal charges, but they're charged compounds. They're the nitrate, sulfate, ammonia, those things. Okay, so you can look at all these examples. I don't want to go through all of them, but I'll go through another couple. If you look here, oxygen. We know oxygen normally has how many electrons? 1, 2, 3, 4, 5, 6. Then we take away how many bonds it's making. How many bonds is oxygen making? 3, so we take away 3. Then we take away how many lone electrons it has. In this case, it has 2, and so it is given a formal charge of plus 1. Does that make sense? This is how we calculate formal charge. The reason this is plus 1 is oxygen here is doing more sharing than we expect it to. We expect oxygen to share only twice and to keep the rest of the electrons. But here it's sharing 3 times. That's where formal charge is a little different. It's not about the number of bonds per se. It's about what the number of bonds and the number of lone pairs says about how many electrons it has in general. So we expect carbon to have 4 electrons of its own. The other way to think about this would be saying, this is like saying 1 electron for carbon, 1 for this other thing. 1 electron for carbon, 1 for the other thing. 1 electron for carbon, 1 for the other thing. So of its own, how many electrons does carbon have here? 3, but we'd expect it to have of its own 4, which means its charge is plus 1. It's formal charge. Likewise, here, this is like saying 2 of its own. Then here it's like 1 of its own, 1 to something else. 1 of its own, 1 to something else. 1 of its own, 1 to something else. So how many of its own does oxygen have here? 1, 2, 3, 4. But we'd expect it to have how many of its own? So it's an electron shy, and if it's less electrons than expected, it is positive. So you can also count it that way if you want. This little calculation here works, or doing what I just did, where you say, okay, lone pairs belong to it. Half of each bond belongs to it. Now we're going to compare that to how many electrons we expect to have. If that makes more sense to you, do that. Did that answer your question? Cool. Right? We can do the same thing with nitrogen here. What's nitrogen's valence? We expect nitrogen to have 1, 2, 3, 4, 5 electrons, right? And then, in this case, it's making 4 bonds and it has no lone pairs. That's a charge of plus 1. The other way to look at this would be to say, okay, this bond is like 1 electron from nitrogen, 1 from something else. This is 1 electron from nitrogen, 1 from something else. Same with those. And that's like nitrogen having how many of its own electrons? But we would expect it to have. So it's got a positive charge because electrons are negative. So if you're shy an electron, you're positive. Whereas in the example above, here nitrogen has 2 of its own electrons, 2 of its own electrons, then this is like 1 for itself, 1 away, 1 for itself, 1 away. And so altogether, how many together? 1, 2, 3, 4, 5, 6. But we would expect it to only have, so it has an extra electron compared to what we expect. So its charge is -1. Does that kind of feel okay? I don't care which method you use. I actually prefer to just count it looking at the structure myself. But if you're the type of person who likes a rule to follow, this is a very easy rule to follow. Valence number minus how many bonds minus how many free electrons, that's the formal charge. Questions about that? Okay, can I move on? We're good? We're comfy with that. Okay, let's go back to our nitrate ion. I want you to calculate the formal charge of each of these things. So the single bonded oxygens, we have 2 of them. There they are. I want to know their formal charge. And the double bonded oxygen, we've got 1 of those. I want to know its charge. And nitrogen itself, find the formal charge of each, please. All right, can you do that? Found the formal charge of nitrogen. Now you got to find the formal charge of all the oxygens. I feel offended. Answer's rude to me. I'm going to give her a harder test than everyone else. Next Monday, but don't tell her. I'm going to throw random Unit 5 questions in there to confuse her. Just. I don't even mark them, I'll just put them in there to stress her out.
Will you actually?
Okay. No, that'd be unkind. As much as I like giving Andrew a hard time, I don't actually like the idea of being unkind to someone. Especially if I happen to really well. No, like these grades now, that would obviously be totally inappropriate. Funny idea. Okay, how are we doing? Have we got these? Or do we not know what we're doing? Because again, what are the steps? We want to find its valence, how many bonds it's making, how many non-bonded electrons. So we'll just remind ourselves valence minus bonds minus free electrons, right? Equals the formal charge. So, nitrogen. Let's talk its valence. What's the valence of nitrogen? How many electrons do we expect it to have? We expect it to have 5 electrons. On the other hand, what about oxygen? How many electrons do we expect it to have? We expect both of these to have 6, because that's the valence of oxygen. Again, let's make sure that's comfortable with us. To figure nitrogen's valence, we just count over. 1, 2, 3, 4, 5. Figure out oxygen's, we just count over. 1, 2, 3, 4, 5, 6. Okay, now, how many bonds are they making? How many bonds is this nitrogen making? Yeah, 1, 2, 3, 4. Doesn't matter if they're sigma or if they are pi. All right, how many bonds are these yellow ones making? The yellow ones. Yeah, this yellow oxygen is only making 1 bond. What about the green oxygen here? It's making 2. Okay. Then, the last thing we need to know is how many free electrons. So how many free electrons does nitrogen have? Yeah, no lone pairs, right? Okay. What's 5 minus 4 minus 0? Positive 1. So nitrogen here has a formal charge of positive 1. Now the other way you could just eyeball that is you could say nitrogen is going to get one of the electrons from this bond as its own, one from this bond as its own, 1 and 1, that's 1, 2, 3, 4, and we would expect it to have 5. Regardless, nitrogen here has a formal charge of positive 1. Does that make sense? Okay, these yellow, it's got a valence of 6. We expect oxygen to have 6 electrons. One of those is being used in a bond here, right? And then how many free electrons does it have? 1, 2, 3, 4, 5, 6. What's 6 minus 1 minus 6? Bless you. Negative 1. These electrons, or these oxygens rather, have an extra electron compared to what you'd expect them to. They have a formal charge of negative 1, which means they are dealing with one more electron than would be expected. On the other hand, this oxygen is making 2 bonds. It has an expected valence of 6, and it has how many free electrons? 4. And 6 minus 2 minus 4 is 0. Okay. Now, what do you note? Well, we note that if we add the formal charges up, we have plus 1, right? Plus negative 1, plus negative 1, plus 0, right? These are our formal charges. And the sum of the formal charges, which I used a sigma there, you don't have to worry about. What is that if you add it together? 1 minus 1 is, minus another 1 is, plus 0 is negative 1. And noteworthily, the negative 1 charge that you get when you add all the formal charges up matches the charge of the overall charge of the ion. So, the sum of the formal charges, I know, but sometimes it's helpful to write something. Let me never be accused of not repeating myself. The sum of the formal charges equals the overall charge of the atom or ion, or the molecular ion, rather. That doesn't feel too bad, does it? Feels okay? Feels reasonably friendly? Friendly? We're good. You got this. Comfy. This is going to become a really important concept because tomorrow we're going to learn possibly the last lesson of the unit, maybe the second to last lesson of the unit, depending on whether I want to get to the last one or not. But we're going to learn about like what happens. How am I speaking here? We're going to learn about what happens when this comes into play, why we would need to know this information. All right? So all we're doing here is we're putting to math something we've already been able to eyeball. If you really look at, for all these fancy numbers, what this is really saying is, wow, nitrogen looks like it's making an extra bond here, right? You'd expect it to only be making 3 bonds and have a lone pair, but instead it's making 4 bonds and has no lone pair. We're just mathematizing that, right? And here we're saying, wow, oxygen's actually making fewer bonds than we expect and has more lone pairs than we expect, right? And all we're doing is taking what we could already see just by looking at it, and we're ascribing a number to it. Does that make sense? We're formalizing something, formal charge, something that we've been able to see just visually. Cool? All right. I want you to try this. Why do we bother with this? Knowing the formal charge is meaningful because they give us an indication of whether or not a structure is likely to actually occur. In nature, structures with no formal charges are always possible. But a structure with a formal charge of +1 or -1 can occur. So if your structure has to give something a formal charge of +1 or -1, that structure can still be legit. That can still happen. They're less favorable, but they can happen. Any structure that requires a formal charge of +2 or more or less doesn't occur in nature. Does that make sense? So if you go to draw a structure and there's more than one possible answer, the one with the lowest formal charge is the real one. In other words, let's draw something that we know the right answer. Right? Ready? CO2. How many electrons does carbon give us? Shh. How many electrons does carbon give us? 4. How many electrons does oxygen give us? 12. Good. For a total of 16. Awesome. Okay. Now we all know the structure of CO2, right? We all know what to do, which is we put carbon in the middle, right? We make single bonds to oxygen. We complete the octets, right? Okay. And then we count the electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, right? So obviously I have to make double bonds. Cool. And so we all know what to do, and we do this. Why not? Why isn't that the answer? How many bonds does carbon make? 4. It likes to make 4. What's wrong? And then oxygen here is only making 1 bond, but we know that can happen, right? Look up here. Oxygen's making 1 bond. That's cool. That can happen. You tell me oxygen can't make a triple bond? Why not? Things make triple bonds. If oxygen can make 1 bond too few, why couldn't it make 1 bond too many? And the answer, by the way, is this is a possible structure, right? It's a possible structure. But of course, we don't actually see this in nature typically. What do we actually see? We see this, right? So the question is, why? Why, put your hand down, please. Why is this the real observed structure? And why is this not typically seen in nature? Well, a trick would be to just say, let's look at the formal charges. Right? Let's look at the formal charges. Let's call this oxygen 1. Let's call that oxygen 2 in both cases. Can we do that? Is that cool? I want you to find the formal charge of oxygen 1, oxygen 2, and carbon for this molecule and for this molecule. Find the formal charge for everything, please. These strings are rough shape. Need to change. Well, what's the rule? You've got to take in each case, you've got to take the expected valence. Then you have to subtract the number of bonds. Then you have to subtract the number of free electrons, not pairs, individually. And that'll give you the formal charge. So let's try that together. Let's see what we get. So we know that we're going to do valence minus bonds, right? Minus free electrons, right? So let's do that for oxygen 1. What's oxygen's valence?
6.
Okay, 6. Minus, how many bonds is this making? 3. And how many lone electrons does it have? 2. Okay, 6 minus 3 minus 2, what's that give us? Nope. Positive 1. Good. Okay. Now let's look at oxygen 2. How many valence electrons does it have? Typically? 6. How many bonds is this making? 1. How many free electrons does it have? 1, 2, 3, 4, 5, 6. And just by visually looking at that, -1. Okay? And then carbon. How many valence electrons does carbon normally have? 4. How many bonds is it making? How many free electrons does it have? For a total of 0. Now, if you take the total of this, if you sum it out, what do you get? 0. And the charge on this whole thing is 0. So this is an acceptable structure. It works. That is a real thing. But if we look at this one, here, oxygen 1, its valence is? How many bonds is it making? How many free electrons does it have? Giving it a formal charge of 0. Oxygen 2 is the exact same thing. So is everyone comfortable if I just copy that? And then carbon, just like in the other one, has 4 valence electrons. It's making 4 bonds. It has no lone electrons, giving it a formal charge. So you're good at this? You got this down? Ready for the test? Okay, then focus, please. Giving it a formal charge of 0. What does that sum to? 0. These are both legitimate structures. They work. We said anything that has formal charges within +1, -1 is cool. But the preferred structure has the lowest formal charges. And you can't get lower than all of them being, so the lowest formal charges are favored. So in practice, this is possible, but it's going to happen, functionally never. Nothing never happens. There's a lot of atoms in the universe. So you can rest assured that carbon dioxide, where one of the bonds is a triple bond and one of the bonds is a single bond, absolutely happens in nature, but it just happens so vanishingly rarely that we can functionally ignore it. Does that make sense? Yeah. If you ask for the structure of carbon dioxide, you'd be wrong, because the correct structure is the best structure, and the best structure is the one with the lowest formal charges. Now, having said that, you wouldn't be wrong if I said, write every theoretically possible structure of carbon dioxide, or write a theoretically possible structure of carbon dioxide, because this is theoretically possible. But if we ask for the structure of carbon dioxide, the correct answer will be the one where the formal charges are lowest. And listen, 9 times out of 10, you don't have to think about it. It's just the one that follows the rules. The best structure follows the rules. The only time you have to worry about it is if you can't draw a structure that follows the rules, like the nitrate ion, or like any of those. Because once it can't follow the rules, now the question is, well, where do I break the rule? And formal charges are going to tell us the best way to break the rule. Because the best way to break the rule is where the least rules get broken. In other words, that keeps the formal charges the lowest. Does that make sense? So again, you didn't actually have to do this for carbon dioxide. How to draw carbon dioxide is obvious, right? You guys all rolled your eyes and groaned when I drew this, right? Because you all knew, that's not how we do it, right? But this shows you why. Because even though that's a possible structure, this is a way more stable structure, which means it's a way more energetically favorable structure. Questions about that? All right. Can we eyeball this? Yeah, like I said, you can absolutely eyeball it. If you draw a structure, you know, if I draw this, right away, you could say, okay, what's nitrogen's formal charge? Well, it's got 2 electrons here, then 1 from the bond, 1 from the bond, 1 from the bond. That's 1, 2, 3, 4, 5. And we expect nitrogen to have how many electrons? 5. So there's no difference there, so the formal charge is 0, right? Whereas sometimes, and this is a real thing, you'll actually get nitrogen attaching to 3 hydrogens in a structure like this. This actually does happen. There it is. When you did this, you'd look at nitrogen and you'd say, okay, what's its formal charge? Well, it's getting 1 electron here. 1 electron of that is its, because again, bonds are always shared, right? So it's responsible for half the electrons. 1 here, and that's a total of how many? Well, it's a total of how many? You're right. 4. 1, 2, 3, 4. And we expect it to have how many? 5. So 1 fewer electrons would be positive 1, because electrons are negative. So if you're comfortable with that, you can absolutely eyeball it. If you're not comfortable with that, just follow the rules and you won't go wrong. Does that make sense? If you're not the type of person who tends to see things and quickly go like, oh, I know what to do, then just follow the rules. Count its valence, count how many bonds it's making, count how many free electrons it has, subtract, you'll get the formal charge. But if you're somebody who's pretty good visually, and you can look at that and be like, oh, I can just count that, then you can definitely do that, but you just got to be careful, because it's easy to start forgetting what you're actually doing. Does that make sense? I've got a little bit of homework for this. I need to copy it over. I didn't print it on your sheet, sillily, but you can check online or you can copy it. Just give me a second. Sorry about that. If anyone desperately needs me to print this, just let me know. This is 1.9, right? And by the way this is drawn, I'll actually draw these in here. But just be aware what's going on here is C. It's being lazy with all these. This would be... So again, you don't have to draw the question out per se, but most of these it'll be helpful. Do you get the idea, or do I need to keep drawing this out? Cool. They just, rather than draw all the bonds to H, they're just seeing C stuck to 3 H's. But really, I wish I'd just drawn it, because you're not as familiar with that. But there you are. Oh, I would love a coffee right now. Let coffee sound good. It'd be helpful if I just printed this.
Is that a C?
Sorry?
Is that a C?
Yes. I'm just going to print this.
No, the third one, sixth one. CH3C triple bond with C.
Where? Which one are we looking at? Here?
6.
Yes, that's a C.
How it's 2.
It's going to have a big old formal charge, isn't it? Yeah, I'll print this for you guys right now. You press stop on the air conditioner. Because as we've all learned the hard way, and by all of us, I just mean me, if I try to run the air conditioner and the printer at the same time, we blow a fuse. Every time. Not some of the time. Every time. Speaking. Absolutely. How many of us are here right now? I'll just do 14, and then we can put them in the handout folder. 15. They'll be back, presumably. Oh. Guys, I desperately don't want to be awake today. Anyone else feel that way? I could just so happily right now curl up and go to sleep. And then in my bio class, like I've got them just working on something today. So that's a nightmare. Yeah. It's just like, it's just so dull. I'm going to be so bored. No, they've done that. No, I'm having them do something that you guys haven't done, which is, if you took it with me last year, we just did our little, like stupid, just learning how to culture bacteria. Not really an experiment, just learning the skill. So I'm going to have them write just an experimental procedure and like a results/observation section. So like their first stab at writing a part of a paper, they're just going to do part of it. No introduction, no discussion, no abstract. I don't think I did that with you guys. Some years I do, some years I don't. Maybe I did. Maybe.
It's not at the beginning. Because I remember we did stuff with like the little dishes.
You did, like you have, I absolutely had you do the lab. I don't think I had you do that for writing.
Oh.
Yeah, I made you keep like a chart, right? Yeah. So these guys, I'm having them actually write me like a little paper.